Alright, in this screencast we're going to look at the beginnings of complex numbers. So a brand new field and an area that we wouldn't have gone down before. We've always avoided this square root of negative field of numbers. We're going to take it on in this section, but we're firstly going to look at some more familiar areas, and that is initially quadratic equations. So solving quadratic equations, we should be really good at that, but we're going to make sure we are, and we're going to have a look at just a couple of examples and how we go about them, and just make sure we've got that checked. We're going to have a look at the discriminant, which may or may not be a new piece of work for you, new area for you, but the discriminant within the quadratics are a really useful tool, and knowing how to find the discriminant and what information it gives you, and then Vietes theorem to do with the sum and product of the roots of a quadratic equation. So let's get down to work. Firstly, quadratic equations, solving quadratic equations. So can we solve quadratic equations? And not only can we do it accurately and quickly, solving quadratic equations. Okay, so the best way of looking at this is obviously by way of a few examples. So let's look at solving 3x squared plus 11x, 3x squared plus 11x plus 6 equal to 0. Let's look at that first. Now what's your method? It's a 3x squared, so I know it's going to be 3x and x. So we could just go in here like this and factorize. I mean, we're always looking to factorize, and perhaps what I need to do firstly here is, rather than assume I can factorize it, let's have a look. I'm looking for two numbers that multiply to 3 by 6, 18, and add to 11. All right, and I know I can see straight away that that's going to be 9 and 2. So that tells me it's going to factorize. 3 times 6 is 18, adds to 11. Those two numbers, 9 and 2. I know it's going to factorize, so I can go ahead and use one of my factorization techniques. Now, because this is 3x squared, I know it's 3xx, so I can go straight in here, and I need two numbers here to multiply to 6 that get me, when I do this and this, I get, when I look at those products, those pairs of products, and add them together, I get 11. So 3x and 2 I can see is going to work. Sorry, 3. So this gives me 9x plus 2x is 11x. So that looks good. So therefore, x is equal to minus 2/3, or x is equal to minus 3. And there's my solution. Another way of doing this, I might not have gone for this approach. I might have gone for all right, let's take the 11x and split it down into plus 9x and plus 2x. So I split it down like that. Remember, the 9 and 2 are coming from there. Then I factorize in pairs. All right, therefore dots to tie it all together. I get the same bracketed expression here, which I can then group together as 3x plus 2, x plus 3. So you might solve it that way. I quite like that way. That's nice and methodical, isn't it? And we're not relying on any of this sort of visual stuff. This is quicker. And as I say, for a prime x squared, that's good. But if it's 6x squared, you don't know what's going to lead each bracket. So you might be better off heading over this way. One or the other, I'm sure you use. How do you know it can be factorized? Well, that's sometimes you're looking at two numbers here that it's not obvious. So another way of checking whether the thing will factorize is to use the discriminant, which we'll talk through in greater detail in a moment. But the discriminant is just the value of b squared minus 4ac. Right, this little triangle here is the symbol for the discriminant. And it's what's under the square root sign in the quadratic formula, isn't it? So in the quadratic formula, you know that you can solve any quadratic using the quadratic formula. We tend not to use it unless we can't factorize, but we can. B, A, and C are all locked in here, aren't they, as A is equal to 3, B is equal to 11, C is equal to 6, so I can put in my minus 11 plus or minus, we could do this. It's not a very clever way of doing it. But 4ac is 4 times 3 is 12 times 6 is 72, so it's 121 minus 72, which is 49 over 6, like this. And what we'll see here is that because that's the square root of 49 there, because of this value 49, that tells me it's factorizable, because now I've got minus 11 plus or minus 7, so I get rational solutions out of this. I get minus 4 over 6, or I get minus 18 over 6, or minus 3, and that's obviously minus 2/3, or minus 3. So we're getting the same solutions there in 3 different ways. But what I wanted to highlight here was this value here. That 49, because it's a square number, means it was a factorizable quadratic. Factorizable because 49 is square. Okay, and actually the value of this here, and this here, in fact, this b squared minus 4ac, that is known as the discriminant. And its value tells us the nature of the solution. So in this case, because it's a square number, it tells us it's going to not only be real solutions but rational solutions. So we can go in there and calculate the discriminant, just b squared minus 4ac, and we can tell if it's a square number, we can factorize. So often we want to know if we can factorize. It's a quick way of doing it. All right, let's have a look at another quadratic equation. Let's have a look at example 2. Let's look to solve. Right, let's now look to solve 5x squared minus 9x minus 3. So I can go in and look at two numbers that multiply to minus 15 and add to minus 9. Nothing jumps out at me, but just to be sure, let's work out the discriminant. The discriminant is b squared, 81 minus 4 times 5 times, so it's going to be 81 minus 20 minus 60, so it's 141. So that is not factorizable because it's not square, not factorizable because it's not square. So 141 is no good. So, but we can still, once we know it's not factorizable, we can go in and use the quadratic formula. So now I just need to go minus b, which is 9, plus or minus the square root. Now I know what b squared minus 4ac is, 141. So it's really useful. If it was square, I'd have gone back in here and I've persisted in here and found those two numbers. As it's not square, I can just use it straight in here into the quadratic formula. So it's a pretty useful thing to do, find the discriminant. So this is my 141. I don't think that can reduce down. So that will be my solution there, my exact solution or solutions to that quadratic. So there's solving quadratic equations. We've started to look at the discriminant. Now, if the value of the discriminant is greater than 0, then what that means is we've got two real solutions. Two real solutions if the discriminant is greater than 0. If the discriminant is, let's say it's greater than 0, if the discriminant is also a square number, so it's greater than 0 and a square number, then it tells us that we've got two rational solutions, and therefore it was or is factorizable. Right, that's useful. The discriminant. If the discriminant is equal to 0, think about that. If this value in here is 0, equal to 0, you've got square root of 0, 9 plus or minus 0. That's gonna rule out the possibility for two solutions. So that just means we've got one solution, or sometimes, as it's known, two equal solutions. Might be worded as such, and in fact two real solutions is sometimes worded as distinct solutions, or distinct roots is also used. Now what about when the discriminant is less than 0? What do we do then? Well, we've got no real solutions, and in fact what we've got are complex solutions. Now what we've done in the past is we've stopped here, dead end, no real solutions, forget it. What we're going to do as we go into this section is we're going to examine these complex solutions. So what is the value, and when x squared is equal to minus 4, let's go into that and represent it as a complex number. Not just yet, but that's where we're going to go with this. So there's our discriminant. There's our discriminant information, and what the discriminant tells us and what the value of the discriminant actually means. Okay, the last thing we're going to look at in this screencast is Vietes theorem. Vietes theorem, which looks at the sum and product. Vietes theorem looks at the sum and product of roots of polynomials. Now what we're going to look at firstly here is a quadratic. So if we're going to say let x1, x2 be the roots or solutions of a quadratic equation, then we're going to say from that x1 plus x2, what's that going to be equal to? What's the sum of those roots going to be? Well, if we look at the x1 plus x2, well, it's going to be, if we look at the quadratic formula, it's going to be, sorry, let's have a look at, right, if it's going to be, one of the roots will be minus b plus the square root of b squared minus 4ac over 2a, that's one of them, and the other one will be minus b minus the square root of b squared minus 4ac over 2a. Now if you put those two together, we've got the same denominator, which is nice. This and this cancel, we end up with minus 2b here, so we end up with minus b over a. Okay, so that's interesting. So the sum of the roots is equal to minus b over a. Now let's have a look at the product of the roots, x1 by x2. What's that going to be? Well, now we just have a look at minus b plus the square root of b squared minus 4ac over 2a times minus b minus square root of b squared minus 4ac over 2a. All right, if we multiply these out, we do this thing here, minus b times minus b is b squared, minus b times this, and this, they're going to cancel, and we're left now with minus, so the square root times square root, we're just left with what's under the square root, over 4a squared, and look at that, the b squareds cancel, we end up with 4ac over 4a squared, which when you cancel that and that and that, we end up with c over a. So the sum of the roots is minus b over a, and the product is c over a. And if we look at how that works in an example, I'll just write it out. Okay, here's an example. The roots of this quadratic equation are x1 and x2. So we're saying these are the roots, and without solving, so we're not going to solve it and then add the roots and multiply them. We're just going to use what we've come up with here, and that is the sum of the roots is minus b over a, and the product is c over a. So the sum of the roots, here we go, is just, what did we say it was? Minus b over a. So b is minus 5, so it'll be minus b over a, which is equal to minus 5 over minus b over a3, so that's just equal to 5/3. The sum of the roots are 5/3. We don't know what they are. That's not important. We want to know what the sum of them are. So 5/3 is the sum of the roots. Now the product of the roots is c over a. So c over a, c is 2, a is 3, so just 2/3. The product is 2/3, the sum is 5/3. All right, what about this one here? C, it says 1 over x1 plus. So here what we're going to do is we're going to, like we would do with any fraction, we will combine them to a common denominator of x1, x2. So on top we'll end up with x2 plus x1. So we end up with sum over product. So we end up with 5/3 up here, 2/3 here, which when you multiply top and bottom by 3 is 5 over 2. And we can do all sorts of different combinations of expressions and tease from those what the sum and products are, and use those values here and here to find them. Plenty more in exercise 3C. So we're now good to go with exercise 3A, 3B, and 3C from the textbook. I'll see you in class.